All right, guys, let's go ahead and come back together. So after this, so we've gone through, like I said, we have to go through step by step. So this is a question that was taken straight from the quiz. This is what it's looking for in the quiz specifically. It's asking for these values. Now, in the process, you still have to find most of the values you would normally, but they're not looking for it as far as an answer. So again, our R total is going to be a combination of the series portion and the parallel portion. The voltage of R1, we take the resistance of that guy divided by our total resistance. The voltage drop across RAB in our potentiometer, we take that voltage, or that resistance divided by the total resistance. The current of R3 is going to be the voltage drop across what is left out of our 47, because we have 47 volts coming in. We have to drop 47 volts across the rest of our system. We have 18 here, 21 here. The rest is being dropped across points BC. Because these guys are in parallel, they're all going to have the same voltage. So then we can calculate the current for R3. And then if we're looking for the power across R4, we can either do it by solving for the current, by taking the voltage divided by the resistance, or just by using one of our alternate formulas from Ohm's law and Watt's law. Okay. Let's see. Any more questions with this? We'll get, like I said, I'm trying to introduce the basics to you guys of the different styles, different ideas, techniques that we're going to use for these. And if you do have questions, feel free to ask. So we need to come back and do some more of these. We can do that. We just got a lot of the basics to at least get through the first time, and then we can go back and hit what you need to. All right. What we're going to get into is more of analysis of a circuit besides design and just solving for things. So we're going to be talking about loaded voltage dividers. So what's a voltage divider to start with? Something that divides voltage. It takes your voltage and splits it up into different parts. When it's loaded, it means we're using it for something. We're not just splitting it up. So our circuit is going to be as follows. Okay, so the idea behind this is we're going to design, I apologize, we're going to design a circuit to accomplish specific tasks. We have two loads that we want to be able to run off the same circuit. The first load requires 15 milliamps at 94 volts. So a motor, a fan, some other system, its power requirements are this. We require 15 milliamps and we require 94 volts. Yes. Yes. RLA and RLB. Sorry. Stands for load A, load B. Yeah. So like if we have a motor and we have a fan. So this is going to be our motor. So we're going to be using it to pump some sort of a liquid through. Let's say we're in a pie factory. So the cream filling, we're making chocolate cream pies today. This pump that's going to be running to basically provide the filling to the other end of the factory, from the big vat that we've made it in, we're going to pump it across to where we're actually going to be using it. We're going to be pulling 15 milliamps at 94 volts. That's what we have to have. Yep. Across this guy, we're going to have 26 volts, and we need 5 milliamps. So here, this is the fan that we're turning on our motor to blow on it to keep it cold while it's running. So, like I said, it's kind of a dumb example, but this is what could happen is maybe as simple as this is we just need to run these off of one circuit. For whatever reason, the bosses said they have to be on the one circuit. We can't build two. So what we have to do is we have to determine how are we going to do this? Okay, so this is where the analysis comes in. What's going on? How do I solve for this guy? Now, this is not a standard series parallel equation. Like, we can't just go through and say, oh, well, this is in parallel with this, except for because it's like this is in parallel with this, which is in series with this, but it's also in parallel with everything else. There's not a real discrete way to say that, this is series, this is parallel. So we have to look back into analysis. So we're going to be using Kirchhoff's voltage law and Kirchhoff's current law to solve for these guys. So with this in place, we know that we're going to be having current flowing through these guys. Also, the other thing that we know is we're going to be introducing another guy that's called IBL, which is your bleeder current. So at the beginning of this week, we were talking about one of our definitions was bleeder current. So bleeder current is current that we have that has to be part of the system. Without this bleeder current, this system won't work. Also, we can check this current right here, and we can verify that this entire circuit is working by one measurement. So the bleeder, in this case, if we're not given a value, we need to assume that our bleeder current is equal to 10% of our load current. Yes. If it's not given to us. Yes.
Is that all the time or just for this schematic?
Well, for this schematic, but for us, for our purposes, we're going to assume. If it doesn't say it, assume 10%. Yes. It's just a standard. Some people want it to be 10%. Some people want it to be 20%, things like that. For our intents and purposes, we're going to assume it's 10%. This isn't like an industry standard or anything. It's pretty much for this class we're making this assumption.
Which means that 90% of the other current is being used.
Yes. Yeah, so 90%. So the current going through here, this is load current. This is load current. So anything that's being used by the load is going to be the total load current. Yes. Yes. And that's the first thing we have to do. Because with this, we don't have quite enough information to solve for the circuit yet. Okay? So to start with, what is our IBL? Two milliamps, because we have 20 milliamps is our load, and we're going to take 10% of that. So now that we have this assumption, we know we have 2 milliamps at that point. Okay, so one of the things I need to figure out is I need to find out how much voltage I'm going to start with, how much this resistor is going to be, how much resistor this, or how big of a resistor that one has to be. These ones assume that they're just coming as is. They come in this little black box. They have 2 wires sticking out. We just have to plug it in. We don't know what's going on inside there. All we know is it's asking for these requirements. Okay? So how do we go through about solving this? Okay? And to find resistance, what do we need? We need voltages and currents. Okay, so we gotta find what the voltage and currents across these guys are. Where would we go from here? Like I want to hear kind of what your guys' thought process are as you're looking at this. Would you? Okay, remember our rules. The rules for parallel and series still apply. Things in parallel will have the same voltage. Yes. You're on the right path. Correct. Then we can find the resistance of that guy. So here, Parallel, these guys are in parallel. We know the voltage here, so we know the voltage here. Things in parallel have the same voltage. So with this guy, so now we know we have 26 volts here. We know our bleeder current is 2 milliamps because of our rule. Okay, what is our total voltage? What's our voltage supply in parallel with? With a 94 volts. So it has to be 94 volts. Yeah, because this whole thing is in parallel with that. So if that is getting 94 volts, that has to be 94 volts. Any questions with those assumptions? Okay? Because again, we have this parallel branch from here to here. We have to be dropping 94 volts. If from here to here we're dropping 26, the rest has to be dropped across there. Okay, and how did you find that? Okay, so also, good, but using Kirchhoff, remember, we have 2 milliamps coming into the node, 5 milliamps coming into the node. We have one path left, so it has to leave the node, so we have to have 7 milliamps coming out of that node. Yep. Mm-hmm. Without this, we wouldn't be able to solve the circuit. That's why we have to make that assumption. A lot of times you're going to come into problems and things like that you're going to have assumptions that are built in that you have to make. So at this point, we're assuming that it is built in there. With that now in place, it doesn't really matter what our assumption is here. It's just we made an assumption, we followed through with it, and with this class, we all know that assumption is going to be 10% unless it states otherwise. Okay. So with this, you could build this circuit. The only thing I would be concerned about is this one and this one. Make sure you have your total voltage correct, and make sure your bleeder current is correct. If those two are right, the rest of your circuit is going to work just fine. That's the cool things about this style of a circuit, is you can build them to where it doesn't matter what you do if this is wrong. Because let's say on this resistor here, it was too big. If it was too big, what's going to happen? If we have more resistance, what happens? Less current. So this is going to drop to 7 milliamps. So if we have less than 7 milliamps, what are we going to have here at our bleeder? Less than 2. So we can check real quick to make sure if we have the proper voltage and our bleeder current, we're done. No, but you could wire them together in series. You can. Some of the power supplies you guys have the capability of spitting out 65 volts. Those are the ones that have the 2 adjustable sides plus the 5 volt in the center. You also have the other ones that we have 4 power supplies or 4 output terminals, and you could technically wire those together. And I think you could get probably, I think it's about the same, about 60, 65 volts if you were to go the max on everything. Mm-hmm. It doesn't matter what kind of power supply you use. It just matters how much voltage you do. That was, remember at the beginning of the semester when we were going through to find out if these power supplies could be series dependent or parallel? That's what it is. So what it does is it allows it to connect it up in series or parallel. Because in parallel, you're going to be drawing more current. In series, you're going to be spitting out more voltage. So it has different internal wirings to help provide either the current or the voltage for what you need. So now that we have those, what is our R1 value and what is our R2 value? for R2? 9 point what? So real quickly, like I said, if this was the problem that our boss gave us, and we have these two components we need to wire together into one circuit, we could do it with this loaded voltage divider. Because we don't really care, like I said, what those workings are. We just know those are our requirements. Okay, any questions about that? Let's look at another one. Okay, so I have something that I need to connect in. Let's say I'm going to need, let's say I need 120 volts and I need 15 amps. And then over here I need 12 volts at 2 amps. So I'm going to run my dryer or my washing machine, and this is going to be my water pump because I don't think the water pump inside the washing machine is big enough. I want, a pump that's going to be throwing, 45 gallons a minute versus that little guy. Yes, we're not jury rigging it, we're improving it. Haven't you guys ever seen Home Improvement? Yeah, his washer and dryer that got put on life support because he overclocked it. Yeah, that's what we're doing. We're overclocking our washing machine. We have to put an external cooling loop because this sucker's going to haul.
Let's go, boys.
Exactly. See, this is the thing. It's easier and it's cheaper to upgrade stuff in your house, and I say upgrade very loosely, than it is to upgrade cars. Because your house, yeah, you can live in it and you can still do things around it. Your car, depending on what it is, you kind of have to fix it before you finish up. So, I've seen people do that. Why not? Have you guys seen have you guys seen upstairs in the lab? Again, that's the reason why. Because there's Nerf guns mounted to wheelchairs. There's Nerf guns mounted to drones. There's Nerf guns mounted to a submarine. I mean, I'm sure they've thought about it. Why not? Again, it comes down into why not. Right, that's probably the reason they haven't. But you build them into a torpedo. Do what? I don't think so. Yeah. This is what we're doing is we're getting this so we fill it up faster and we drain it faster, so it doesn't take as much time in between loads. In this case, yes. So that's what we have to determine. Where is our bleeder current going to go? What's the definition of the bleeder current? Current that's not being used by the load. So we have two options to put our bleeder current. It's still going to be 10%. So our bleeder current, where is the current going to be that's not going to be used by the load at all? It's going to be R2. Because if we had it up here, we have current coming up this direction from our load. So this is going to be a combination of that load current. So bleeder current does not ever get seen by the load. Ever. It's completely independent to the load. Because this has Okay, so go ahead and go through this and let's solve it. I want to know what my voltage total is. I want to know what my voltage, current, and resistance are for each of these two guys. So this is the first one that we have to look at. Okay, where does my bleeder current go? And I'm glad you asked that question, because it could go either spot. And for these, like I said, it doesn't really matter what the load is. I'm just giving you ideas of what things are that we could be designing this for. It could be an ice cream maker and a pump to fill the ice cream maker up from a 55-gallon drum of mix, all running off of the same circuit. Well, you weren't here for the day that we built the power supply that was like the. Yeah, it was. What we? Yeah, it got named the face of God because the flash of light that would have happened would have been so bright you wouldn't have been able to see anything else because it probably would have burned out your retinas. Watch the videos. But like I said, that's because again, it just comes down to that's kind of one of the whole points with this program is because like you guys are like, well, why would you do that? Well, why not? That's
Because we would die.
right. So there's your why nots. But the thing is you can do whatever you want with this. That's the whole point that I'm trying to teach you guys.
Can I overthrow the world?
You probably could at some point.
I know what I'm going to do with my computer.
So, because like I said, that's so guys, as you're working through this stuff, always keep in the back of your mind, okay, be thinking of something that you want to do. Because we have opportunities throughout all the different semesters for smaller projects until you get into 4th, 5th, and 6th semester. So if there's things that you guys want to build or have ideas for, like be thinking about it because there could be a way you could implement that and have it as your project when you get into the upper semesters. Because like I said, with mine, it was we built a foosball table. We kind of had this idea that we wanted to do that to like the air hockey table that we have in there that one side would play you. And so we didn't get it to actually work. We had bugs in our code somewhere that was burning stuff up. Electronically, it worked just fine. It was in our code that we screwed up. Okay. Give you guys about another 30 seconds to finish up where you're at. Or this could be a washing machine in your camp trailer. Because you run off the 120 volts, 15 amps, and you have your 12-volt battery running the rest of it. All right. Ugh. Too old for this. So what is our load current? Okay. How much is our bleeder? 1.7 amps. What is the voltage across R2? 12 volts. What's the value for R2?
7.05 ohms.
How much power? Nobody did. I'm just asking now. That's why.
Well, is 20.4 watts. There's a lot.
There's a lot. Okay. What is the voltage drop across R1? 108 volts. How much is the voltage of our supply? 120. How much current do we have going through R1? 3.7. What's the resistor we need? 29 point what? And how much power do we have across that guy? Yes. They do make components that are up that high. A lot of, like you're saying with your elevator parts that you have, some of those they have resistors. You know, they're tubes this big. Lots of ice cream. Okay. So again, this is just the applications of the laws that we've been learning about for all these different circuits. So we've got series circuits, we've got parallel circuits, we've got current voltage law, Kirchhoff's current law, Kirchhoff's voltage law. Everything is being built together into these guys. Okay? Do these make sense? Right. No, and I get that, and that's what I'm trying to figure out is where do we need to cover again? Okay. That's why we try to do a couple of these each time, just so we can get a feel for what we're looking for. Because again, it comes down to what are we looking for, what do I need, and how do I get there? So it's going to be based on everything you know. Okay. So do you get where the voltage for R2 is? Okay. So when we look from this point to this point, what's our voltage? 120, because it's in parallel. This point and this point is in parallel with that guy. So we should have 120 volts. So if we know that this voltage here is going to be in parallel with this one, we know we have 12 volts here. From here to here we have 120. If I have 12 there, how much do I have here? 108. Because going straight through this, that's just a series circuit. Huh? One current path. Yes, it does branch, but we're just looking at this in terms of voltage. In that case, it just becomes a series circuit. Okay. Should I make you guys squirm? No, I won't make you guys squirm. Okay, so the idea is go through these quizzes. So far we've talked about, I think, 3/4 of the quizzes that are available. I can't pull up the list right now, but it's all the math except for factoring trinomials, which I'm trying to get the steps to get this so it's easier for you guys. I still struggle with factoring trinomials, just so you know. It's not something we use a lot, but it is something that does come into play. So other than the factoring trinomials quiz, and then the loaded voltage divider and some of the troubleshooting, we haven't gone over those, or the bipolar voltage divider. So this is what we're going to do tomorrow. Huh? It's two of these together. But there's so many moving parts, so that's the thing, is we have to keep track of it. Okay, guys. Also, remember, I am available for help if you need it. You can stick around after class. I can answer questions for you. I will be in my office till about 5 today. If you have questions, please feel free to reach out. Did anybody try to get a hold of me today while I was gone? Okay. I thought I had everybody's phone numbers or as messages coming in, trying to make sure I answer when I can. So, again, I apologize for lab. Won't have to happen again for another 2 months.